The last concept we need to cover in subtopic 2.3 on work, energy and power is about efficiency. This video should be fairly quick, considering that this idea is something you will have covered in say, Year 8 or 9 science. And it deals with any type of energy conversion. And so when any energy conversion occurs, and just a reminder here that when we talk energy conversion, we're either talking a transfer or transformation of energy. So in any of those situations, we have some of the energy will be lost. And by lost, and I'll put it in inverted commas here, we don't mean that it disappears. It means that we've lost it to forms of energy that are no longer useful. And usually, we'll see in most processes, the forms that where it's not useful are usually going to be heat and sound. Now, there are other situations where lost forms of energy can be different. It could be light, could be even kinetic energy, some of those sorts of ideas. But ultimately, we're just looking at the fact that the energy that we start off with that's useful, and the energy that we end up with will usually end up with less useful output than we had to start with. Now, I could go through a few different examples here of thinking of things like a ball bouncing. So when a ball bounces, initially it's GPE converted into kinetic energy as it falls, and then when it hits the ground, the kinetic energy, some of it is lost to heat, so with the deforming of the ball and the transfer through friction to the ground, can also be lost to sound, so some sound waves being produced. And so when the ball then bounces back up, so I should also mention there elastic potential energy as the ball's bouncing. When it bounces back up again, the ball will then end up not getting to as great a height as it did initially. So the final GPE will be less than the initial GPE because of these forms of energy where where energy has been lost to those forms. Could also look at things like, say, a stovetop. You've got electrical energy being put into the coil on a stove. If you then have a pot that's sitting on top of the stove, some of the electrical energy that's going in, some of that will be simply just will be heating the coil itself. Some of that heat will then be lost to the environment, while some of that heat is then actually transferred into the pot itself, and then through to the food there as well. So again, we've got this lost form of heat. So the electrical input that we have, or the electrical energy that we have to start with, will be greater than the heat energy that's supplied to the food in the pot, and so we don't have 100% efficiency. We're always going to have less than that. So, like I say, there are a number of different examples that we could refer to, and we'll have a look at a few in class and identify where the energy is lost. But ultimately, we're looking at the efficiency of those processes, and the efficiency of an energy conversion is a pretty simple calculation. And that equation, basically just write it in word form. There isn't a shorthand way of writing it that's a common way. So efficiency is equal to the useful work that you get out of a situation, or the useful energy. So the useful work that you get out divided by the total work that you put in, or the total energy that you put into situation. I'm using the word work here because that's what's used in the data booklet, but ultimately you could look at the energy forms there as well. Now, if we consider that power is equal to work over time, so in the case of looking at work, we could say that work is then equal to power multiplied by time. The useful work that we get out, that time factor will be the same. So if we consider it over 1 second, for example, compared to the total work in, so again, total work in, power multiplied by time, consider it over 1 second, we can then also look at the fact that it's the useful power that you get out over the total power in. And as I said, that is an important equation that's in the data booklet, so I'll just go through and highlight that whole thing. So fairly straightforward calculation. You just need to know what you start off with, what you end up with. It's useful in order to calculate the efficiency of that scenario. One last point there too, that value of efficiency can be expressed as a decimal. So that equation that you can see above, that will always give you a decimal value, and just as a side note here, it will always be between 0 and 1, or as a percentage. So converting from the decimal to a percentage, just multiply by 100 in order to get the percentage efficiency, and it's quite often the more common one to say that something's 50% efficient or 75% efficient, rather than just it has an efficiency of 0.5 or 0.75. We'll have a look at a few questions in class about efficiency, and then that will wrap up subtopic 2.3.